Hello, everyone, and welcome back to your, to your channel of basic engineering. Today, I will start the last topic in the course of statics, which is belt friction. So, to understand what's happening here is that basically you will have like two pulleys here, one connected to a motor and another one maybe to a blower or something in a furnace. And once the motor rotates, the belt will rotate. Keep increasing the speed, and the belt rotates faster and faster until we reach a point where the belt will start slipping and not rotating with so it slips over the pulley, usually the smaller one. At that point, where the the belt is about to slip, we call it the point of impending slippage. And that's what we are going to analyze so that we come up with an equation that relates the two tensions in the belt. Meaning, if there is a friction here, the tension on the right will not be the same as the tension on the left. Okay? So what's going on? Think about it. If that pulley is rotating counterclockwise, which side do you think will be pulled more? Higher pull. Counterclockwise. So if you turn like that, even if you think about it from a non-engineering point of view, you would say, okay, if this thing is rotating like that, it's pulling this piece, the right-hand side, more, and it's like pushing the left-hand side. So common sense would say the right-hand side would carry more tension than the left-hand side. Okay? So now we are going to take a very small piece, P prime here, enlarge it a little bit, and let's assume the angle, well, I don't like the term d theta. I would call that delta theta. Likewise, since as you go from the left to the right, the tension increases from T2 to T1. So from P to P prime, the tension on the right would be slightly more T plus delta T. Okay? Now, there is a normal force, of course, going perpendicular here. So if we call that axis the y-axis, and this is the x-axis, and this angle is delta theta. So this would be delta theta over 2 on the left and delta theta over 2 on the right. Again, I'm going to call that delta n and delta f. And we know that at the point of impending slippage, delta f would be mu sub s times delta n. Okay? Now we're going to take that and analyze it, start to come up with an equation for the belt friction. So let's take the summation. First of all, we have this equation, as we always say, delta F equals mu sub S times delta N. And this point is the point of impending slippage. Then we have two more equations of equilibrium. As you know, in friction at the point of impending motion or impending slippage, now we have three equations of equilibrium. This is one, and then delta X summation of the forces in the X direction equals 0. Let's write in the X. This is the positive X. So I have T plus delta T. So notice again, like we said, that, let's see. Yeah, if notice that here is the pulley. So this is important. When it turns like that, the belt want to keep it from turning, right? There is a friction. And the friction, it means that the friction opposes the direction of rotation on the pulley. The friction force is an internal force. It always comes in pairs. If it's going clockwise on the pulley, it must be going counterclockwise on the belt. That's why delta F is drawn to the left here. Okay, so at this point, delta F is exactly along the X. So you can say negative delta F, or like I usually do, I'm going to move it to the other side and say delta F equals, I have T plus delta T times cosine of this angle, cosine delta theta over 2, okay, minus T cosine delta theta over 2. So of course, T cosine minus T cosine cancel, and I can rewrite it as delta T cosine delta theta over 2. But delta F is mu sub S times delta N. So we can write this as mu sub S delta N. And this is my first equation. My second equation is the summation of the forces in the y direction equals 0. I have delta N going up. So I'm going to write delta N. And then since it's already going up, I'm going to move everything else to the right-hand side, meaning anything going up would be negative, anything going down would be positive. We don't have anything going up, but we have T. So T plus delta T again, T plus delta T, but this time it's sine delta T, delta theta over 2, plus T sine delta theta over 2. Notice that these two equations, the one on the top has a mu sub s. So let me multiply everything here by mu sub s, mu sub s, mu sub s. Okay? Since these two are the same, it means that this equation equals that equation. So I'm going to write delta t cosine delta theta over 2 equals all of that. Notice I have mu sub s t sine plus mu sub s t sine. So that becomes 2 mu sub s t sine delta theta over 2 plus delta t mu sub s sine delta theta over 2. So far, so good. I'm going to divide everything by delta theta, okay? So I'm going to divide this by delta theta, and I'm going to divide that. I'm going to make it a little different. You will see why in a second. I'm going to divide that by delta theta over 2 times 2. Okay? And I'm going to divide this, same thing, delta theta over 2 times 2. Then I'm going to take the limit as delta theta approaches 0 for everything. Oh, I should have left enough space. Let's look at the left-hand side. The left-hand side, as delta theta approaches 0, then cosine delta theta over 2 is cosine of 0, and cosine of 0 is 1. When we say the limit of delta t over delta theta, we call that dt d theta, right? That's the definition of the differentiation. Let's move to the right-hand side. I know that the limit, notice that 2 mu sub st over 2 is a constant. But the limit as delta theta approaches 0 of sine delta theta over 2 over delta theta over 2 is 1. So that gives me There is no limit now. I can write mu sub s times t. Okay? And that's why I wrote this as delta theta over 2 to match the angle inside the sine. So I have to multiply it by 2, and the 2 and the 2 cancel, and I end up with that. Okay, now, again, delta sine, the limit as delta theta approaches 0 of this guy is 1. But now, if delta theta approaches 0, then delta t also approaches 0. So this whole thing will go to 0. And I end up with this equation. Well, that's a differential equation. You can just, and it's separable. So you can say dt over t equals mu sub s d theta. And then, like you learn in the, well, even if you didn't take a course in differential equation, it's so easy here that you have to integrate both sides. You integrate both sides by going, the t goes from t2 to t1 because you are starting from the left, and then when you move to the right, you increased it a little bit. So now this integral is from t2 to t1, and theta goes from whatever angle it is, so like theta 1 to theta 2, okay? If you call that angle theta 1 from here to here, and goes all the way to here where there is the tangent, that would be theta 2. Now, if I integrate, the integral of the left-hand side is the natural log of t. Well, I don't need that because the tension cannot be negative, so I don't need the absolute value, but it's evaluated from t1 to t, or from t2 to t1. Well, some people use t2 as the higher of the two, and others use t1 as the higher of the two, so it really doesn't matter as long as you know what you're doing. And this guy would be mu sub s times theta 2 minus theta 1. Usually, the difference in the angles, we refer to them with the letter beta, with angle beta. That's, usually engineers use beta as this angle going from here to here. Notice, this is the radius at the point of tangent, of where the belt is about to leave contact, and here also it is. So theta 2 minus theta 1 is this angle. Okay, so this becomes natural log of t1 minus natural log of t2. We know the laws of natural log. If you have a difference of two natural logs, you can write it as natural log of t1 over t2 equals mu sub s times beta, and then you exponentiate both sides. You get t1 over t2 equals e to the mu sub s times beta, or t1 equals t2 times e raised to the mu sub s times beta. And this is the law that is similar to that law in the dry friction. So in dry friction, we say that. In belt friction, we have this equation is the third equation that we use. Okay, having said that, I'm going to take a problem, solve it with you, an example to solve it with you. And then in the last session, I'm going to take another problem with two pulleys of a motor and some kind of a pulley. And then, as I promised you before, I will give you a problem where there is belt friction, there is dry friction, and in dry friction, we are going to consider sliding versus tipping. So we cover everything, one generic and complete example. Here's an example. In this example, it tells you, well, we can make up some missing information. It doesn't matter. We have here what we call a band break. It's you know, there is there is a pulley here that can rotate clockwise or counter. It's connected to a motor that can rotate clockwise or counterclockwise. Okay, and in each case, if you want to stop it, you can push this handle up. So when it goes up, it pulls this side and increases the friction until the friction is so high that it stops the band brake. And that point would be a point of impending slippage, meaning if you release the force a little bit, the pulley will start rotating again. So they are telling you what is the maximum, what are the values of the tension in this type of belt? Uh, if you are applying, or how much rotation, how much torque can you stop if you apply a force of 200 Newton to this handle? Part A, if the pulley is rotating clockwise, part B if it's rotating counterclockwise. And they tell you that let's say mu sub s here is 0.3, and they tell you the weight of this handle is not negligible. Okay, so it is 15 Newton, just 15 Newton. And now we need to solve to find what is the maximum torque T that we can stop. So first of all, we can assume something. So part one or part A, rotation is clockwise. Okay, so this band brake is rotating or the pulley is rotating clockwise. Before solving clockwise or counterclockwise, we can consider the free body diagram, the free body diagram of the handle. Okay, so I think it's here. We have the handle. I really don't need some forces in the X or the Y. I'm only gonna take a moment. I'm gonna take a moment to find out. Okay, so there is a T here. At this point, it doesn't matter. There are an X component of the reaction, a Y component of the reaction, and a tension. So I just gonna say, if we call that point B, for example, and this point A, and this point C, I have BX and BY. You say, what about the tension? Well, the tension has an X component and a Y component. So at the end of the day, I get those. As you will see, I don't care. This is 200 Newton. It looks like a 3 anyway. And then here, midway, there is the load, or the weight is 15 Newton, and here is a T. Okay, let's write the dimensions. From A to B is 675. Where did I get 8 millimeter? From B to C, it's 75. And from C to the end, it's 150. So if you add them up all, you get 675 and 75 is 750 plus 150 is 900. So the load or the weight is 450 from here. And since this is 675 minus 450 is 225 from here, from there. And just to tease the graders, the teachers and professors, I'm not going to draw summation of forces I'm not going to show the X and the Y coordinates. And you say, why? Say, because I'm not going to teach it, use it. I'm sorry, I said teach it. Take the summation of the moment about point B, because where B, I have Bx and By, I don't need them, and equate that to 0, and counterclockwise is positive. The 200 is going counterclockwise, and it's 675 away. So 675 times 200, that's a positive moment. The weight is negative, so minus 15 times 225 clockwise, so minus 75 t equals 0. All these numbers are divisible by 25. You can simplify if you want, or you can use the calculator and get done with it. I mean, it's not worth it. So you're going to say t equals, when you move it to the right-hand side, becomes 75t. So I'm going to evaluate that and divide it by 75. I'm going to say it's 675 times 200 minus 15 times 225, close parentheses, divided by 75. I get 1755 Newton. Notice that whether the pulley is rotating clockwise or counterclockwise, it doesn't matter. T will never change because T depends on the force I'm applying, which is the 200 Newton, right? But when the rotation is clockwise, come to think about it. When the rotation is clockwise, this part is pulled more. So that would be T1, and that would be T2. So now I'm going to draw the free body diagram of the drum, of this drum. So basically, you draw a circle. I hope this will draw. Okay, not bad. Say this is the origin O, and I have a vertical piece. If we assume T1 is greater than T2, as I said, some people do it the other way around, but since here in the previous thing we said the higher, we called it T1. So if we are rotating clockwise, this would be the higher, so that would be T1. And that here, oops, is T2. The radius is 0.15 meter. Right? It's 150 millimeters, so 0.15 meter. Because usually we are not going to report the torque in Newton millimeters. So let's go ahead and use that. I know the equation said T1 equals T2 times e to the 0.3 beta. I know T1 in this case, I need the smaller one. 1755 equals T2 times e to the 0.3, and now I don't know beta. How do I calculate beta? Notice beta has to be in radians. I've seen students using an angle, say, of 200 or 270 and raise e to the power of, oh my God, like 81 if it's 270, and you get a huge number that doesn't make sense. How can you stop that torque with a small force with your arm? It's so please be very careful. This is like a fatal mistake if you use degrees. So you have to use radians, okay? Once you find the angle, if you don't have even radians in your calculator, which I doubt anybody doesn't have it, but just multiply by pi over 180. Okay, so now we say, what is beta? Usually the books will tell you, which is correct, by the way. First of all, here is the theta 1, that's the point where the belt leaves the drum, okay? And here is the other thing, and this angle is beta. They give you this angle to be 60 degrees. Notice I didn't need to do it here because I didn't use a summation of the forces in X and Y, but the angle is 60 degrees. I will need it here. If this angle is 60 degrees, and we know that the radius is always perpendicular to the tangent, so if I make an angle, a horizontal line here, I know that this angle is also 60 degrees, right? They are alternate internal. And if this is 90 and that's 60, so this is 30. And what is this whole angle now? Okay. If you don't see it, I usually explain it to my students in a slightly different way. I say, assume that you bring the cable in your hand and let it look like that. So this line here is my cable. And then I'm going to rotate it about the drum. If I rotate it like that, it's 90 degrees. If I rotate it like that, it became 180 degrees. And then I'm going to rotate it through this angle. You see, this is 180. I'm going to rotate it through this angle. So if this is 60, that would be 30. And this whole angle would be 210 degrees, which is 7 pi over 6. I know many students have trouble finding this angle. It is this angle. Like we said, okay, if you extend this line, remember we said this is 60, alternate internal is 60, this is 90 degrees, so that's 30, alternate internal, so that's also 30. So you have 180 plus 30. This is the angle that you rotate around. Okay, so times 7 pi over 6, meaning I'm going to divide 1755 by that. So T2 equals 17, oh, we already have it, it doesn't matter. 17 divided by second E raised to the power of 0.3 times 7 times pi over 6, close the parentheses. And I get 584.44 Newton. Now, we need to know what type of a torque or what magnitude of a torque can I stop or can I handle with a force of 20 Newton? If you know this T and that T, how do you find the torque? Very easy. You take the moment about 0.0, right? Summation of the moment about 0.0 equals 0. This guy is rotating clockwise, so it's a negative moment. T1 is rotating counterclockwise, so plus 1755 times the radius, right? The perpendicular distance for both of them are the radius. So in fact, I could have said 1755 minus 584.44 times 0.15 equals 0 to get it in Newton meter. Instead of saying 1755 times 0.15 minus 584.44 times 0.15, I just combine them. And now I can say this number minus that number times 0.15. I get 175.6 Newton meter. That's the clockwise moment you can stop by applying a force of 200 Newton on this band brake. Now, part B or number two, counterclockwise rotation. So easy, because now you see that if it's rotating counterclockwise, that would become T1 and that would become T2, but the magnitude of T1 becomes the magnitude of T2, which is the 1755. So really, all what you have to do is to take the same number when you took T1 equals T2. The only thing is that instead of making this T2, that would be T1 and that would be T2. So you would be multiplying instead of dividing. So all what you have to do is to say, take the 1755, and then instead of dividing it, you multiply it by uh, what is e to the power of 0.3 times 7 times pi over 6. And you get 5270. So T1 here would be 5270 Newton. And the torque, or the moment, is basically would be this 5270 minus 1755 times 0.50. So we switch. When the bigger one was 1755, of course, the other one would be smaller, and the torque you can stop is small comparatively. But when the 1755 is the smaller tension, then T2 would be a larger value, and you should get a much bigger uh, torque. So we are going to say this number minus the 1755. Well, again, I could have said, just type it, times 0.15, and we get, no, but it's, yeah, 527.2 Newton meter, which is roughly 3 times more, okay? So that's basically it for today. Please understand how when it rotates clockwise or counterclockwise, which side is heavier or which side has a higher tension. It's so easy when you come to think about it. Think always that if you are rotating clockwise, you are pulling this piece, so it has more tension. It's stretched more. If you rotate counterclockwise, then definitely the inclined part would be the part that is carrying more load. I don't need to find the tension here. I don't need to analyze some of the force in the X and the Y. In fact, you can't, because you don't know the magnitude of the tension. All what you know is that its X component equals BX on the pin, but you don't know in either. So you have to analyze by using the moment, finding the tension in the vertical piece only. And that's all what you need, because you can find the other one based on the rotation. Okay? I hope this was clear. Next time, as I promised, that would be the last lecture in this course. I will do 2 more problems. And one of them, as I mentioned, would be combining dry friction, belt friction, slipping versus dipping, and everything. So thanks for your time and hope to see you soon. Have a nice day.